Vicky, hello. That's right. Similar to last time, I've prepared a lot of material for our third session out of 6 on the Kea DHCP server. And today we will talk about lease allocation, meaning when DHCP request comes in, how Kea will look for free leases, how client classification works. We talk about DHCP options, that is how we send configuration options back to the client to configure the network stack. We see how DHCP reservations works in Kea, and we have a short part on a shared subnet. And as always, we have then question and answers at the end. So first, let's start with lease allocation. And here we see a simplified diagram that shows how Kea would choose a lease. It starts that a DHCP lease request comes in, and then Kea checks if that request contains a client ID. And if it contains that client ID, it will check whether there is already a lease that can be identified by that client ID. If a lease is not found, or if the request doesn't have a client ID, it then will go forward and find a lease by the hardware address. So it looks for whether there is already a lease for that hardware MAC address. And if that is not the case, then it will look for all the free leases available. And if there are no free leases available, it will send back a not acknowledge, telling the client, no, we don't have any free IP addresses for you. If any one of the green boxes in the middle are successful, then Kea will process the host name, if there is any. So there could be a host name being sent by the client in the request, or there could be a host name in a reservation, or there could be a rule that Kea creates a dynamic host name. And then optionally, it will update the DNS, reflecting the assignment of the IP address to the host name, and then send an acknowledge back to the client. If we look deeper into how new leases will be found, that is, if there's no existing lease for the hardware MAC address or the client ID, then Kea first checks whether the address has an address hint. And an address hint would be an IP address that the client previously had, which might be expired, but could still be valid. And if there's such a hint in the request, Kea will first check whether that address is still free. And if it could be found, if the old lease could be found, then it will recycle that lease and will return the same IP address that that client had before, even though the lease had expired in time between. If we can't find the lease candidate from the hint, we will create a new lease. If there's no hint in the request, then Kea will go through all the subnet and pools configured. And we talk about the order in which that happens in a moment. And it will then pick a free address. And then it needs to check if that address might be reserved, because Kea allows for DHCP reservations to be inside a pool. So there could be a pool of addresses from a starting address to an end address, and there could be still some addresses from that pool being reserved for particular hosts. So Kea must check whether that is the case. And if it is reserved, it needs to go back to the beginning and start looking for another free address. And if it is not reserved, then the new lease is being created. It's being stored to storage, either to a database or to the lease file. And then the lease is being returned to the client. So how Kea is searching for a new lease, that changed with the latest version 1.8 that has been released just a few weeks ago. because Kea 1.8 iterates over all subnets by the subnet ID. And previous versions iterated over the subnets in configuration file order, which could lead to the effect that you created some new configuration or changed your configuration, and that in subtle way could change how the lease being found. And by doing that by subnet ID is more stable. So in DHCP, we have this idea of client classification, which is realistically more a packet classification, but most people use that to somehow classify the client that is sending the request. So Kea DHCP can assign one or more client classes to a request. And then depending on in which client class the request is in, the DHCP server can fill in different information into the response being sent out. And that could be different DHCP options. It could be special IP addresses that being selected depending on the client class. And it could be boot P parameters in DHCP v4. So for example, a common use case is to select from multiple available and possible subnets or pools with the help of these client classes, and we have some examples coming up. These client classes can be built from various DHCP identifiers. And identifiers here is some information that is in the incoming DHCP request package. So it could be any of the information that has been sent from the client machine. It could be information that had been added by a DHCP relay, and it could be information how the packet reached the DHCP server, for example, on which network interface it reached the DHCP server. So client classification really looks into the DHCP packets, the content, and then selects one or more classes. So here we have the sources of DHCP identifiers. So it could be from the host, and the host can send client options, so the number of options the client is requesting, the hardware address, which is the MAC address, a client ID, one vendor option that identifies the vendor of the machine, or the host name that the client is sending. Then a DHCP v4 or DHCP v6 relay could add additional option and additional information to the request before it is being forwarded to the DHCP server. And we can even nest the relays as in DHCP v6. So we can have a number of DHCP relays that not directly sent to the DHCP server, but one relay sends to another relay. So we can have hierarchical structures of relays, and every relay can add its own options to the packet. It's like an onion, so every DHCP relay adds another layer of nested options. And then the DHCP server can look at all the layers and can make client classification decisions based on that layers. And identifiers can come from the server itself. So for example, the network interface over which the packet reaches the server, or the DHCP server's destination address. If the server has multiple IPv6 or IPv4 addresses, it might be interesting from what address the packet is coming in. Some vendor classing, some client classing happens automatically. For example, Kea DHCP automatically assigns a vendor class if the request contains a vendor option. And that dynamic class, that client class, is being prepended with vendor underscore class underscore, and then the content of the vendor option. So for example, if we have an option value DOCSIS 3.0, which is common in modern cable modems, then the packet automatically belongs to the class vendor underscore class underscore DOCSIS 3.0. And that makes for an easy way to distinguish between different types of devices in your network. So here we have an example configuration for Kea DHCP v4. And it selects different IP addresses depending on the vendor class. Now, in this example, the vendor classes being used are just examples. They are not the real world values that you would see. But to have it more visible, more easy to recognize, I use these values. So there's a vendor class Windows CE, which is kind of a portable, maybe point of sale Windows device that runs Windows CE. And that sets that client class. And in the first subnet with the 192.0.2 addresses, if a client comes in with that vendor class, it gets an IP address from that range and that pool. And it gets the router, the default route, the default gateway that is shown here in the option data. And if the vendor class is Fedora Linux, it gets a completely different subnet, and with that, different options, different pools, and so on. In addition to the automatic vendor classing, Kea can also automatically assign classes based on reservation, and these are the known and unknown classes. So every client where Kea will find a host reservation, that client will be automatically in the known class. Known means here, I know that machine, I know that MAC address, I have a reservation for that. And every client that doesn't have a reservation will end up in the unknown class. And then in the configuration, you can distinguish between known classes or known clients, which might be internal machines, machines belonging to your organization, and other machines that are guests. And then you can, on the wireless, for example, distinguish between them and give them different security configurations. For example, guests could directly go out to the internet, while staff people have to use the mandatory proxy to go out for security reasons. And the most flexible way to do client classing is to use expressions. And with the expressions, you can really look into the packages. You can inspect any strings that are in the request. You can even look for bit patterns, for options that are available. So you can almost extract any information from the DHCP request, and then you can even group and assign these expressions and put them together to have multiple inner lines to assign the classes then on the request. And the list of available expressions that you can use to look into the request package is quite large. I have the link here to the Kea documentation. And on the next slide here, we have a part of these expressions that are available. So for example, you can look at whether an option exists in the request. You can look at the binary data in the option, in the string representation of the option, the interface name of the package, the source IP address of the package, and so on and so forth. So this is really very, very flexible. And here we have an example of client classing. And there are two client classes. One is called Windows and the other one is called Others, because all the Windows machines, they send a vendor option, option 60, that starts with WIN. And in this case here, if we see a request coming in where the vendor option starts with the characters WIN, that's a Windows machine. So we place that in its own internal DNS domain called win.example.com. And in the second client class, we negate that expression with the not. So we look for the substring in option 16, the character 0 to 3. And if that is not WIN, then it's in the other class, and it gets the domain name other.example.com assigned. Besides selecting different options, client classification could also be used to select a different subnet inside a shared network. Now, we will talk about shared networks at the end of this webinar, but in short, a shared network is when you have different IP address subnets on the same physical network. And here we have the 192.0.2/24 network, and that is for all the client class, the Windows client classes. And then we have the 10 all 0/24 network on the same physical subnet on the same interfaces. And that is for all the other machines, the non-Windows clients, and they get IP addresses from that. So that makes it, for example, quite easy in the firewall or in log files to distinguish accesses by Windows clients versus any other clients. Now, client classifications, if you have to use a complex expression, like I want to check whether option Y starts with this characters and option X shouldn't start with the others, and it should come in via that relay, and it should reach the DHCP server over that interface and so on, then it can slow down the server if the expressions really become very complex, because for every incoming DHCP request, Kea must go through all the expressions and evaluate the expressions. It's something that is done during runtime, and that can hurt the performance. And the alternative here would be to write a custom hook for client classification, which is actually then that you cast your rules for client classification into a compiled extension of the Kea DHCP server that will be then loaded into Kea and runs in maximum performance time. So you use the C or C++ programming language to do that. That's a little bit more work than using the expressions, but it is much, much faster for complex expressions. If you have a lot of expressions or complex expressions, sometimes it's hard to figure out why is Kea selecting certain options or doing certain client classing, especially if you might have expressions that contradict itself or cancel each other out. So you want to debug what's really happening here. You want to watch Kea by doing the evaluation and see how it comes to the verdict of selecting one client class over the other. And there are multiple options how you can do that. One is the quick option is to stop Kea and then start Kea from the command line in debug mode, and that will print all the debug output and a lot of information about how Kea does the client classification directly on the terminal. However, if you have a busy server with hundreds or even thousands of requests every second, that will be too much debug information to even read. So there must be, so this is an option for a Kea server in a test lab or in a network that is not very busy. If you have a busy server, you can extend the configuration, the logging configuration of Kea, and enable the Kea DHCP v4 or Kea DHCP v6 eval debug logger. And that will log only the evaluation, and it will log only that one into a dedicated log file, while the debug mode, of course, enables debugging over everything Kea does, and then you don't see the wood because of all the trees. But with this logging, you only see the evaluation being done, and that's much easier than to figure out what Kea is doing internally and where your configuration might be wrong. Yeah, and then you look into the log file and you see hopefully how it works, and you get a hint how you can restructure your configuration to achieve what you want to do. So that was client classification. And now we come to the DHCP options, and DHCP options are basically all the configuration stuff that we send back from the DHCP server to the client that helps the client to join the network and reconfigure the network stack, and maybe even configure some of the applications running on the client. And we can, in Kea, define the DHCP options in different scopes. There's the global scope that is then an option for every DHCP request is coming in. We can have on the class scope, meaning we have a client classing expression somewhere. We define a class that the DHCP request is in, and then depending on the class, certain DHCP options get assigned. We have options on the subnet and pool level and on the reservations. So here we have an example of a global DHCP option. This option is for the domain name servers, and it's for DHCP v4, and it's in CSV format, which is the basic text format of Kea. And then the data field contains really the option data to be sent back. And this is the most verbose way of defining DHCP options. But luckily, all the fields have sensible defaults. And if we are fine with the defaults, we can just omit the fields like code, space, and CSV format. And then it's much nicer to read and less clutty. Here. So we just define the option name, which is domain name servers, and we define the data that should be sent back as the DNS resolvers in the network. And here we have an option defined in the subnet. So it's the 192.0.2.0/24 subnet. It has a pool, and for every IP address that is being given back from the pool, every lease that is being assigned, we send back the default gateway with the routers option, and we send back the domain name, which is the a.example.com in this example here. And this is the example using a client classification. And here we look if the vendor class identifier is Putzio, whatever that means. If that is the case, it gets a different or a special option called the log servers, and then the IP address for remote logging. Kea already supports a lot of options, hundreds of them, but sometimes it's required that you define your own custom DHCP options, because there might be some options that are vendor specific, options that are not in the standards. And you can do that, of course, with Kea DHCP. So on the global level, you have an option def statement that defines the name of the option, the code, the type, or whether it's an array of multiple values or just a single value, in which option space it lives, and whether it is encapsulated. And then you just define, once you have defined the option, you can just use the option with the option data statement in the same way that you use the built-in options. It is possible to define conflicting options. That means the same option but different data for the options on the different levels. So you can have here in the first line, there is the DHCP option domain server. And that is defined on the global level, on the network level, and on the subnet level. And the different scopes are being evaluated from left to right. And the option scopes that are more to the right have the highest priority and will overlap or replace all the options that have been set before. So in the second row, where we have the host name being set on the network level, on the pool level, and then on the host level, meaning on a reservation, then the reservation wins. The static route can come from a client class. That is the one client class, and because a package can be in multiple classes, there can be a second class, class N in this case, that also defines a static route. And then the second one wins. So if you have multiple client classes and they have conflicting options, then the client class wins that are assigned in the order of in which the client classes are being evaluated, and that is the order in how they are specified in the configuration. So I think this is very important to understand that there is a scope order, and I also see most often that customers have issues in this case because they end up with options that they don't expect in the DHCP response. And also the evaluation logging will help here, because in the logging you see in which order Kea go through all these scopes and at what level different options are being assigned to the DHCP response before it is being sent out. So now we have a look at the DHCP reservations. With DHCP reservations, we define that one machine always gets the same lease IP address. And that reservation can be either on a client ID, or it can be on a hardware address, or it can be something else, some identifier. And reservations are being done because of security policies. For example, there's a firewall rule that allows a certain IP address to do more than others. And in order for that machine to make use of that firewall rule, it always needs to have that one IP address that has more access than the others. Also, if you use DHCP to distribute IP addresses to your servers, instead of doing static configuration, that's possible. Of course, you want to have your servers stable addressing. Your server should always get the same addresses, and DHCP reservations is one way to do that. Some software products have licenses that are bound to IP addresses. So the application running on top of the machine only have a valid license if the IP address is the one that is registered for the license. So you always want to have that machine have the same IP address. And also with reservations, it is possible to create a simple captive portal in the way that if a request is coming in from a machine that is not known, that doesn't have any reservation, it is being placed in a subnet where it can only go to the captive portal or web page and can register itself. And then the captive portal web page and the web application running behind that, after successful authentication of the user, will place a reservation for the MAC address for that one machine that just authenticated into the Kea configuration, and that turns the machine from an unknown client into a known client. And once it is in the known client class, it will get different DHCP options, a different network, and that network will allow the machine to really participate in the network and communicate with other machines. And of course, there are possibly more reasons why to use DHCP reservations. So we can create reservations based on the MAC address, on the DUID in DHCP-v6, on the relay circuit ID for DHCP-v4, or on the client ID or the host name for DHCP-v4, or the flex ID. Now, flex ID is a special hook into the Kea where we can create IDs based on anything that is in the package, the request package. And that is how the name implies, a very flexible way to do reservations. Now with reservations, we can not only define the IP address lease that should be given back to that machine, but also certain other DHCP parameters such as the host name, any of the DHCP options, reservation client classes, and for bootp, the boot file name, the next server, and the server host name. Now, the question is, where should we define the reservation? And Kea is also quite flexible here in such that it allows DHCP reservations on the global level and on the subnet level. Global reservations are interesting for cases where you want to assign certain DHCP options, for example, a fixed host name, but not IP addresses to a client, because then the client will always get these options, and it will always get these host name, independent in which network the client is roaming in. On the other side, it is often not really sensible to define IP addresses for leases on the global scope, because then the client might be in a network and sending the DHCP request from a network where that one IP address doesn't really make sense, or the default route doesn't make sense. So the client will end up with a non-working network connection. And Kea will not prevent you from making this mistake, because Kea has no way to figure out whether a global reservation really is sensible or not. So the common case is to have the reservations if they contain IP addresses, either on the subnet or on the shared subnet scope. There will be a change in Kea 1.9 insofar that it will allow reservations to be defined both on the global and on the subnet level itself. So for the same machine, you can have global reservation for some DHCP options, and then on the subnet level, you define certain IP addresses that the client should have depending on the subnet it is in. So here we have examples of global reservations. The first one is on a hardware address, and we define a specific host name for that machine that comes in with the AABBCCDDEEFF MAC address. The second one is also on a MAC address, and we give it both a host name and a fixed IP address, and it says risky at the end, because this only works if that host also gets or is already in a network where that IPv4 address is being usable. And the last line is an example on a reservation based on a circuit ID, So that identifies not the single machine, but the network where the machine is in. So we give back the host name. Also in reservations, it is possible to have in-pool and also out-of-pool reservations. Now, what is an in-pool reservation? An in-pool reservation is an IP address being used in a reservation where that IP address also falls into a dynamic DHCP pool configured in Kea. That's possible, but if you have such a configuration, then whenever Kea is assigning an IP address leased from the pool, it must double check whether that IP address is also a reservation. Because if it is a reservation, it cannot give that IP address to any client. It can only give that IP address to one specific client. So this requires an extra check inside Kea that makes lease allocation a little bit slower. On the other side, if reservations are only outside the pool, and that could be, for example, that you split a subnet into two parts. One part of the subnet is the dynamic pool, and another part of the subnet is where the reservations live, and these two parts don't overlap. Then you can tell Kea that you will only use out-of-pool reservations, and whenever Kea is picking a free IP address from the pool, it does not need to check whether there's a collision with a reservation. We talk about this in the DHCP tuning part, also in this webinar. So where do we specify the reservations? For small deployments, small, I would say a few hundred machines, you can just write the reservations inside the configuration file, and that is good. And you could even script that part so you generate the reservations. You don't type that with a text editor, but you have some kind of scripting, and that creates from maybe an Excel spreadsheet or from an IP address management system, create this configuration file for you. But on larger deployments, it might be easier to change the DHCP reservations dynamically and programmatically with an API. And that is what the host commands hook is for, and that is a premium hook that's not for free, but not very expensive, that you can buy from ISC to expand the functionality of Kea. We look into this a little bit. If you want to use the host commands, then the reservations are being stored in an SQL database, and we will cover SQL databases with Kea in the next webinar. So it doesn't work with the writing to a text file. It has to be an SQL database. But it could be that you specify reservations both in the config file and in the database, and then the reservations in the config file have priority over those in the database. So with the database and with the host commands, you have a couple of API commands like reservation add, which will add a new reservation. You can fetch all the defined reservations from the database, either a single one or every one, or you can even page through it, which is useful if you write your own web interface for management of the reservations. And you can pick a reservations by a host name or by client ID. And of course, you can delete reservations. And here we have an example how that works. This is a snippet. It's a JSON, JavaScript object notation, which is the internal language that Kea speaks, and also the Kea configuration files are in the JSON format. Here we write something like this into a text file. It's the command reservation add. It's for a DHCP v6 service, and we create a reservation on the DHCP unique ID, on the DUID. We give a host name, the IP address, and two options that we want to send out. And this all should go into subnet number 1. So this is a subnet reservation. And so once we have written that in a file, we can use any tool that can send the JSON request to the API endpoint. Here I use the curl command line tool. You could also use Kea shell or any other tool that can do HTTP posts. And the result is here being piped into the JQ tool, and JQ just pretty prints the JSON output. And the output here is result is 0, and 0 is always the successful result. And we have a host added to the system. Here's an example how to retrieve all the reservations. We give the service which we want to address. We give a command and the subnet from where we want to have the reservations. And then we use curl and we specify that JSON file towards the API endpoint, and we will get a long list. I think that's in the no, it's not here, but you could then you get a long JSON output with all the reservations in there. So we can also do client classing in reservations, meaning that whenever we have a reservation and we have identified a client by hardware address or client ID or any other means that is possible for the reservations, we could assign that client to one or more client classes. So in this example here, we have the machine that has a specific hardware address that should belong to the client classes Windows and staff. And then somewhere else in the configuration, we then assign options or other configuration parameters depending on these two client classes. So about the performance tuning, in the default mode, when you don't change any of the configuration, Kea does the most checks possible to prevent lease conflicts with the reservations. But that is also the most slow mode. It's probably not a problem if you have a moderate busy server, but if you have a server that is hammered by thousands of clients, then performance tuning might be a good idea. For example, if you don't use any reservations and if you do everything from a pool, you can just switch off all the checking that Kea would do to figure out whether a pool address is also in a reservation, and that is reservation mode disabled. And you can specify that globally or on a subnet or in a shared subnet, telling Kea, in this subnet, there are no reservations. So just skip all the checks, find a pool address and return them. And here we see the currently 4 reservation modes that are available. All is the default, where reservations can be everywhere in global subnet or in the pool scope, and all the checks are enabled. We can define reservation mode out of pool, telling that reservations in the subnets should never be inside a pool, but always outside, so that the special check whether a reservation conflicts with a pool address can be skipped. We can also specify that reservations only live on the global level. So all the checks that are required to prevent conflicts on the subnet and pool level are then being skipped. And we can disable that, and that is for the best performance. But you should only use that if you really don't use any reservations. There's a second part where you can tune the performance of reservations, and that is the type of identifiers. Now, again, the identifiers are the bits in the request through which Kea will identify the reservation. Most people use hardware addresses, that is MAC addresses, but others might use DUID, client ID, circuit ID, or the flex ID. Kea, in the default case, must support all of them and have to check for all of them if they are available. And checking for all of them is also slower than not checking for some of. So you can tell Kea which kind of identifiers you use for reservations. And then Kea will only check and will only extract these identifiers from the incoming packages. In this case here, in this example, we check only for circuit IDs and hardware addresses, but not for DU IDs and not for the flex IDs. And you get the best performance if you limit the identifier types ideally to just one type. And that was reservations. And now for the last chapter in this webinar, that is about shared subnets. Now, a shared subnet is if we have a physical subnet where we usually would only have one IP network in there, but instead we have multiple IP networks there. In a shared subnet definition, we can have either 2 or even more subnet definitions. And in such a shared network, we can have then pool definitions, subnet definitions, and options. And if we don't use any client classification, then Kea is just free to use an IP address from any of the pools inside the subnets inside the shared networks. So if you have shared networks and you have 2 subnets with pools in there, and the client request comes in, you might get an IP address back from the first one or the second shared subnet. If you want to really be sure that certain clients only get IP addresses from one subnet inside the shared subnet and the others from the others, then you have to use client classifications. Most people don't need any shared subnets. Now, shared subnets are more of a hack in cases where, because of some circumstances, there is a need to have more than one logical network in one physical subnet. Reasons could be that there was once only one IP network on the subnet, and then that was full, and it was not possible to expand the address range for that subnet. So a second network would had been assigned to the same physical subnet. So now we have 2 different subnets, but on the same range, and the DHCP server must deal with that. Other use cases are where we should want to give different IP addresses from different subnets to different types of network devices. One example would be routers, like residential CPE routers versus the client machines, the desktop machines and laptop machines. Or we want to separate between mobile machines and desktop machines, or we want to separate between point of sale devices and some IoT devices. That is also possible. Here we have an example of a shared subnet. It starts with the shared networks control statement. We give the shared network a name. It's called Kea Lab 01 here in this case. And inside we have 2 subnet 4 definitions, one of the 192.0.2 with its default gateway option, and the second one is the 10.0.0/24 with a different default gateway option, of course. And then we have each of the subnets have their own pools. So, and that concludes the 3rd part of this webinar series. The next one coming up is on 28th of October, the Kea DHCP with high availability, that is failover and load balancing and the database backends. There where we discuss how to store configuration, leases, and also reservations that we have seen already today, how we can store that in the database. Then on the 28th of November, we talk about monitoring logging and Stork, which is a graphical user interface front end for Kea. And the last one is about migrating to Kea from the ISC DHCP server and best practices and how you approach such a migration and yeah, what tools are available to help with that. So here we have some resources about the stuff we talked about in this webinar for you to dive deeper into the topics. And now let's see if we have some questions that we might be able to answer.
We have a couple of questions that it looks like Tomek is starting to answer in the chat. One question about shared subnets. Can shared subnets use overlapping IP ranges? Tomek, do you want to speak to that as opposed to my just reading your comment here?
Yeah, sure. Kea doesn't support it. And can I ask the person that asked this question to explain what is the scenario when this would make sense? So some parts of the Kea code, they are trying to find a subnet based on the IP address. So if the same address belongs to multiple subnets, this would make some of the assumptions incorrect. So, and in normal networks, subnets cannot overlap. So the only case when it would make sense is something that we call multi-tenancy. Like, for example, you have multiple hotspots and you want every single hotspot use the same private IP addressing. But this is a scenario that is not supported by Kea yet.
I guess the question is, maybe the shared subnets, the name could be called as a subnet collection. The word shared makes it ambiguous there. What it means is, can you come to that mean?
I'm sorry, I didn't get that.
Roma, your audio is very low. Maybe you could just try again, or maybe type your comment, either one.
Yes, the wording shared networks there is a bit misleading. Is it more like a collection of subnets rather than shared subnets?
Okay, so
yes, Tomek, please.
Okay, so the original idea behind shared networks or shared subnets, this is basically a different name of the same thing, is that you have certain part of your network, Ethernet segment, let's say, and you assign a subnet, and then you run out of addresses. So you want to add another subnet on top of it. So topologically, both of the subnets are in the same place in your network, but they are using different IP addressing because you no longer have a subnet big enough to contain all the addresses, or maybe you don't want to renumber the old addresses that are already assigned. So this is like a way of saying to Kea that, hey, those two subnets are really physically in the same place. So if you run out of addresses from the first subnet, it's okay to use the second one.
Okay, that explains it. Thank you.
So we have another question from Ben. Does configuring IPv6 follow a similar configuration topology to IPv4?
Yes, so in principle, Kea, the V6 implementation and V4 implementation in Kea, we try to make it as close as possible. From the DHCP perspective, there are some slight differences. The biggest one is that in V6, the protocol is using DUID identifier instead of MAC addresses. The second difference is that if you have multiple relays, in V6, the packets are encapsulated one within another. But from the Kea configuration, this is almost transparent. So, and finally, the third difference is that in DHCP V6, you can delegate, obviously you can delegate single addresses, but you can also delegate whole prefixes. So this is called prefix delegation, and this is a unique IPv6 feature.
Yeah, but from the configuration, it's almost the same, except for where the protocol is a little bit different.
Yes.
So we have just one more question. It's fairly specific. It's from Jeff. He addressed it to just the panelists, so everyone else doesn't see the question, I'm afraid. But apparently in ISC DHCP, option 12 is presented even if there is an option 81, and in Kea, option 81 overrides option 12. And he was asking if it's possible to present option 12 in preference to option 81 when you have both of these. This is a FQDN option. Does anybody know the answer to this? It's fairly specific.
Okay, so I cannot answer it precisely, but I can point you to a couple things that you can do. So you might define a host reservation, and then you can govern which option is sent back. Okay, so maybe this wouldn't work for FQDN. There's flex option. This is something that you could configure to tweak behavior of standard key, I would say. So you can say that you want to set a different value of an option, or even say that you don't want an option to be sent back. So this is one thing, and also there's many configuration knobs for the FQDN, for the DDNS subsystem. So I'm not really expert on this part of Kea, but you might take a look. And also I know that there were some improvements done in the 1.8.0 series. So make sure that you look at the latest version.
Sure, this is 1.8, and I looked at the documentation. It's identical to 1.6, where if there's an option 81, it always overrides option 12. And ISC DHCPD honors 12 unless you turn on option 81 handling. So in our test labs, we get a bunch of duplicate host names from these clients who are simply appending a host, simply appending a domain onto their host names as they send them an option 81. So we get a lot of double subdomains. In other words, a printer might come up with a name of NPI 1234556, and it gets a DDNS entry of NPI 1234556.my.net.my.net, because that's what the option 81 says, whereas option 12 just has the host name. It's okay if folks can't answer up to it. That's okay. I can wait for other improvement, but I'd like to be able to make it act like DHCPD. Okay,
so Jeff, can I ask you to open a ticket for this in our GitLab? So sure. then we can follow up.
Yeah, I've got sniffer traces at the ready, but I figured that since we were having this meeting, I'd ask, and then I will open a ticket. Thanks.
Thank you.
Okay, that, oops, we have, do we have any more questions? No, I think that's it for the questions. And we're just at the hour, so we're done for this week. I just want to remind everyone that the next webinar is taking place after the daylight savings time change for Europeans. So please check the time. So that you, the webinar is scheduled on North American time. And so we're gonna have a mismatch for the next webinar. I apologize, maybe I haven't put that very clearly, but just make sure you check the time for the next session. Anything else? Okay, then we're done. Thank you very much, Karsten, for another good webinar.
Thank you. Thanks for everyone attending and listening, and see you next time.